Semiconductor Packaging. John D. Thomas, Alex Ruth. Book 2, Section 1, Chapter 6, Topic 2. Understanding the ideal and typical response of power delivery networks considering component parasitics. Introduction. The power delivery network, PDN, is a critical aspect of electronic systems responsible for supplying stable and reliable power to integrated circuits, ICs, and other electronic components. However, the response of the PDN is influenced by various factors, including parasitic elements associated with the components used in the network. This overview explores the ideal and typical response of PDNs considering the effects of component parasitics, including resistance, inductance, and capacitance. It examines how these parasitic elements impact PDN performance, stability, and efficiency, and discusses strategies for mitigating their effects to optimize power delivery in electronic systems. Ideal response of power delivery networks. The ideal response of a PDN refers to the theoretical behavior of the network under ideal conditions, where all components exhibit perfect characteristics and no parasitic effects are present. In an ideal PDN, the supply voltage remains constant regardless of load variations, ensuring stable and reliable power delivery to ICs. Key characteristics of the ideal PDN. 1. Zero resistance. In an ideal PDN, the resistance of power traces, vias, and interconnects is negligible, resulting in minimal voltage drop across the network. This ensures that the supply voltage remains constant at all points in the circuit, regardless of load currents. 2. Zero inductance. Ideal PDNs exhibit zero inductance, meaning there is no energy storage or magnetic effects associated with the conductive elements. As a result, there are no transient voltage fluctuations or ringing phenomena caused by inductive effects during load changes. 3. Infinite capacitance. In an ideal PDN, the capacitance of decoupling capacitors and power planes is infinite, providing an infinite charge reservoir for supplying instantaneous current demands. This ensures rapid response to load changes and minimal voltage droops or spikes during transient events. Typical response of power delivery networks considering component parasitics. In real-world PDNs, the response is influenced by various parasitic elements associated with the components used in the network, including resistance, inductance, and capacitance. These parasitic effects introduce non-ideal behavior and can degrade PDN performance, stability, and efficiency. Effects of component parasitics on PDN response. 1. Resistance. The resistance of power traces, vias, and interconnects introduces voltage drop and power loss in the PDN, leading to reduced supply voltage levels at the load. Higher resistance values result in larger voltage drops and decreased power efficiency, particularly in high current paths. 2. Inductance. Inductive effects in power delivery components, such as power traces, vias, and package leads, result in energy storage and magnetic coupling phenomena. Inductance causes transient voltage fluctuations, ringing, and voltage overshoot during load changes, affecting signal integrity and stability. 3. Capacitance. Capacitive effects in decoupling capacitors, power planes, and interconnects influence the PDN's ability to supply instantaneous current demands. Capacitance provides charge storage and filtering capabilities, reducing voltage droops and noise on power lines. Mitigation strategies for component parasitics. To mitigate the effects of component parasitics and improve PDN performance, several strategies can be employed. 1. Low-resistance materials. Using low-resistance materials for power traces, vias, and interconnects minimizes voltage drop and power loss in the PDN, improving power efficiency and signal integrity. 2. Decoupling capacitors. Placing decoupling capacitors strategically near high-current load devices helps compensate for voltage droops and noise on power lines, ensuring stable and reliable power delivery to ICs. 3. Power plane design. Designing power planes with adequate capacitance and low inductance reduces transient voltage fluctuations and improves power delivery efficiency in the PDN. 4. Impedance matching. Matching impedance between power delivery components, such as decoupling capacitors and power traces, minimizes reflections and signal distortion, enhancing PDN performance and stability. Conclusion. In conclusion, the ideal and typical response of power delivery networks are influenced by various parasitic elements associated with the components used in the network. Resistance, inductance, and capacitance introduce non-ideal behavior and can degrade PDN performance, stability, and efficiency. Understanding the effects of component parasitics and employing mitigation strategies, such as using low-resistance materials, decoupling capacitors, power plane design,
and impedance matching, helps optimize power delivery in electronic systems and ensure stable and reliable operation of integrated circuits. By addressing component parasitics, engineers can design PDNs that meet the stringent requirements of modern electronic applications, including high-performance computing, telecommunications, and automotive systems. Thanks for watching.
Please like, share, and subscribe.